If you have a table of contents, you can compare it to this one.
Okay.
If you have a cover, it'll look like this. Just say functions 11.
Let's see.
We'll have no problem with this, Natalie. No,
I
just
hope
trust. No,
so, like,
just trust me.
it's
Oh, it's overwhelming, and you're like, "What the hell is she talking about?"
for sure.
Yeah, just
Yeah.
do the homework. Stay on top of the homework.
Especially because, like, last
So you're cutting out a bit. Say it again.
she said that last semester, like, 1/3 of her class failed a
Oh, that's
textbook
great news.
class.
That's nice of her. Well, yeah, but you're a smart cookie.
I
So
know.
if you stay on top
Like,
of it,
so many people I know failed.
yeah, stay on top of
Yeah.
it. Yeah, I think it's
Yeah,
easier
true.
if you find a question you did in class and we see if it matches.
Well, wait, I just pulled it up right now.
All right.
It's like loading.
I know,
It
but
just
we
takes
don't.
so long to load.
It's low. It's taking so long
Okay,
to load
chapter
because,
one.
yeah. What's the first words you see?
Chapter 1, notes or exercises.
Oh, okay, that's her doing though.
Chapter 1.
We need something that
Okay.
I think it's smarter if you find a question she did in class, right?
Uh-huh.
And then we'll see if it matches this textbook. Like if she did
Okay.
question 2 or gave you a number. So,
Yeah, it doesn't even tell me.
no, I know.
But what's it called? So what do I give you a question that we did in class?
Yeah.
Okay. Let me look for my notebook.
It'll be something like state which relations are functions or use the vertical line
yeah.
test.
Yeah, it was mostly like should I give you like an equation?
Yeah.
Or like
So
because what we do is like we look at the functions and we try to like find the domain and range.
Yeah. So give me an exact question she asked.
Is each relation a function y equals x minus 5?
Hang on. Stop. Just a second. It's not that. Oh, I got 2x minus 5. Okay, what we're going to do, I'm going to stop my sharing. Do you see at the bottom of your screen that you can share?
Yeah.
Okay, share your screen. There we go. I'll let you know when I can see your screen.
Okay.
You gotta choose your screen. There you go. Now let's start your screen sharing.
Can you see
Okay,
it?
yeah, but I only see my big face. So click on, there we go. And I'm going to turn off my video for now so that
Okay.
we don't, let's see if I can figure out how to do it. Okay, good. So, course, workspace, content, assignments, workspace, yeah, function. Click on that 1.1 for me. 1.1.
This one?
Yeah.
Or this one?
No. That's fine. Whichever one. That one's good. Scroll down. Scroll down. Okay, click on the next one. Oh, stop there. Let's see. Let me see those images right there. So you see how it says page 11? If you look up top, it says page 11. Okay, let me see one of those images. Yeah, keep going. There we go. Don't move. Yeah. Okay. It looks like she's not taking it from there.
We didn't do that though.
No, I know, but I'm just trying to see if it matches the textbook, huh? So it doesn't matter if you did it because she's going to do it. Now, if you go back up, so go click on the image on the right there. No, on the right. Yeah. See there? It says 1, page 11. So, yeah, it's not from page 11. Let me open the other textbook and see.
Okay.
Because there's 2 possible textbooks, right? Someone just is texting me. I don't know why. Oh. Okay, so I'm just going to pull up my own math of 11 and see if it's this one.
Okay.
Just stay there. Stay where you
Wait, what
are.
about this one, Pete? What about
Let's
this
see.
one?
Let's see. Page 10. Yeah, that's a good one. Stay there. Stay there for a second. Don't move. Page 10. See if this is. Yeah, this is not it. That's not it. So it's definitely going to be that. -5, 1. I think that's it. Just a second. Yeah, well, it's hard, eh? If we don't know where she's teaching from, it's hard for us to stay ahead of it. But that looks familiar. Just stay there for a second. -5. I think she took that right from the beginning. Yeah, I don't have the same thing though, but it looks so familiar. -4 to 0. I wish I knew where she was taking that from. So I'm going to take a screenshot of that and see if I can figure out exactly. So we're going to just have to go. Let's go with what your thing is. So she just went through this, but I see those are questions. Doesn't she want you to answer that, or you're not there yet?
Yeah, we kind of did this in class. She didn't assign any for homework, but like in class we did.
Okay. And what didn't you grasp? I'm going to stop your sharing. Is there anything you didn't get, or it's just like, oh my goodness, it's all kind of overwhelming?
It's like overwhelming, but like right now we recently did like honestly it's all just overwhelming and like I just don't
Okay.
understand like
Yeah, but it's
I'm
just,
not confident in it.
yeah, you're not going to be confident. Okay, so can you see my screen now?
Yeah.
What I'm going to do, I'm just going to get rid of my ugly face so that it doesn't use up too much. Let's see, hide self first. I'm going to stop my video. There we go. See, this way we won't use up too much bandwidth. So you can see the screen here, right?
Mm-hmm.
So let me explain the whole purpose of a function. If I know that on Tuesday it's going to rain, and on Wednesday it's going to snow. Friday, it's sunny. Let's say that happens every Tuesday, Wednesday, Friday. If I know it's Tuesday, I can tell somebody says, hey, Natalie, it's Tuesday. What's going to happen? You're going to say, it's going to rain. Or if someone says, hey, Natalie, it's raining, you can say, it's Tuesday. Right?
Mm-hmm.
Why? Because there's a relationship between Tuesday and that it's going to rain. Wednesday. If somebody told you it's Wednesday, you would say, what would you say if it's Wednesday?
Oh, it's going to snow.
Yeah. How did you know that? Because Wednesday it always snows. What if someone says to you, it's snowing? What would you say?
Let's say it's Wednesday.
Exactly. This is a connection, even though this is not realistic, right? You have information that tells you the other information. But if I did this, Saturday, it's going to snow. And I said to you, hey, Natalie, it's snowing. What would you say?
Say it's Saturday?
Well, but isn't Wednesday it's snowing as well?
Yeah, so it's Saturday and Wednesday.
It's Saturday or
I mean,
Wednesday.
wait, it's Saturday or Wednesday.
But that does me good. That does me no good. Because I need to know a specific day. This is an example of a relation where I can get 2 possible answers. And this here is an example of a function in which I am certain of my results. So a relation doesn't do you as much good as a function. And in science, we turn everything into a function. If we can. Because then it's predictable. We can predict what will happen in certain cases. And this is why in your textbook, if we look, and we're going to just work from this textbook because we might as well, they try to explain to you, okay, with this. Now, my example is pretty loose because we're going to come across something. There are two ways of figuring out if something is a relation. One is called the vertical line test. You draw a vertical line like this. You see it? And you move left and right along the graph. And you see how many times that red line crosses the blue graph. How many times does it cross the blue graph?
1.
Therefore it's a function. What about here?
1.
Right. Therefore it's a function. Now I'm going to draw my own graph in blue and pretend it's on. Here, I'll do it over here. You tell me what this object is. Oops. This is a very useful site, by the way. Okay, what kind of object is that?
Circle.
Right? Look at this formula. Try to sort of memorize that that's always going to be a circle. And we're going to go back. How do I get out? I somehow got into... There it is. Okay. Now have a look at this. Does this graph pass the vertical line test?
No.
So it doesn't. There's two separate top spots and two separate... There's a bottom spot and a top spot where it crosses. That means, for instance, if I said when x is 1, if I asked you when x is 1 right here, and I asked you what y is, you'd say, well, y is either here or y is here. And you wouldn't be able to tell me, like, whether it's snowing on Wednesday or Saturday. You can't tell me properly what that x leads to. So if I say, where does x lead me? Where does x of 1 lead me? You'd say, well, it either leads you here or here, but I can't tell you which. So that is not a function because I cannot predict where I will end up when x is 1. It's either here or there, but that's no good for my weather system. So what they're trying to teach you is what graphs are a useful predictor and how can we define it. So let's go back and have a look and see at these numbers. Now that's the vertical line test is obviously a very easy way to measure, isn't it? Just take a vertical line test, do it, you're done, you got your answer. But when it's numbers, it's a pain in the butt. So for numbers, we have to look at the numbers specifically. And don't worry, these are similar examples your teacher gives you. Just like here, we have to look at the x. So we can see x is 1. And this x of 1 leads to where? What's the y? It's always x comma y, by the way. X comma y.
4.
Yeah, this x of 1 leads to 4. But isn't there an x of 1 over here?
Yes.
What does it lead to? That's right.
9.
And what you do for functions is you don't focus on the y. You focus on two x's that repeat. And if those same x's give you two different y's, it is not a function. That's not true for y. For instance, you can have this. Let's say instead, this said 5 comma 4. You'd say, oh, there's another y here. It's repeated. But that's okay because the x's are different. So if I were to graph that, this x of 1 leads to the y of 4. But this 5 over here also leads to 4. And that's fine because they would pass the vertical line test. If I were to put this here, it only crosses that dot once and that dot once, so it passes the vertical line test. But if I put what they originally had, let me graph what they originally had. They had 1 comma 9 and 1 comma 4. Well, 1 comma 9 on a Cartesian is roughly there, let's say. And 1 comma 9 is way up here, isn't it?
Yeah.
So if I were to put those two dots there and take a vertical line test, doesn't that red line cross those two dots at the same time?
Yes.
So it's not a function. So it's possible to graph those dots and see, oh, those two x's lead to that same x of y, or sorry, that same x of 1, that same x of 1 is leading me to 9, and it's leading me to 4, right here. Well, that's not a function because that same x can only lead to one y. Okay, so when you're looking at numbers, you look for repeating x's. And if you see repeating x's, yeah? Repeating x's, then, yeah, I thought you asked a question. If you see repeating x's with different y's, it is not a function. Some of these you just have to recognize. What the heck? I'm going to send you this as well. And it's this. It is a list of parent functions. And we can see, here's a typical one. What's that look like? It's a line.
Line.
And what if I put a 3 in front of it? Oh, it changed, didn't it?
Yes.
Okay. But a line would pass the vertical line test, wouldn't it? Like I could draw a vertical line through that. It'll pass. Wouldn't it?
Yes.
If I took a picture, don't guess, by the way. If anything, anytime you don't understand, you want to stop me and say, I don't get what you're saying. So if I were to take a picture of that and draw a vertical line, it's clear a line passes the vertical line test, doesn't it?
Mm-hmm.
So a line is a function. And we should just recognize what lines look like. Lines have an x that only has a 1 as an exponent, or nothing. And they can have a number here, but you're always going to recognize it like this. Now I'm going to go back to our textbook. Doesn't that look like it potentially is a line?
Yes.
We see an x with a number beside it and then another number. Let's see what that looks like. Y is equal to 3x minus 5. Doesn't that look like a line?
Yes.
So all we have to do is recognize a function. A line will always pass a vertical line test with one exception. What do you think what kind of line would never pass a vertical line test? A vertical line
Oh, vertical.
will never pass a vertical line test. So anything that says x is equal to a number is a vertical line. But guess what? A horizontal line, which is y is equal to any number, does indeed pass a vertical line test, which makes sense because it's a horizontal line. So the only line that never passes a vertical line test is a vertical line, no matter what number we put.
Okay.
Right? But it makes sense.
Yeah.
All we have to do is recognize what a line looks like. A line always has an x with 1 degree, which means one exponent of 1. It might have a number in front of it, which is its slope. And it might have a number over here, either minus or plus. And that's its y-intercept. Y is equal to mx plus b. So it's important for us to revisit our lines. Now let's look at some other functions. Don't worry, I won't get too complicated here. Let's go with this. That looks sort of familiar. This is called a parabola.
Parabola?
Yeah, but won't a parabola always pass a vertical line test if I take a picture of that
Yes.
and do a vertical line? I think the parabola passes the vertical line test. Yeah, it's only crossing the parabola once. So if I can spot a parabola, I know it's a function. A parabola will always have an x squared. Sometimes it'll have a number in front of it. Sometimes it'll have a number added to it. But it will always pass the vertical line test. Sometimes it looks like this. This is called a standard form parabola. But it's still a parabola, isn't it?
Yes.
And it will always pass a what?
Vertical line test.
Right. So if we can spot the formula of a parabola, we're fine. We're going to skip these other ones because they don't always pass a vertical line test. They always do, sorry. And so it's an x cubed and an x to the 4 and an x to the 5. They'll always pass a vertical line test. And then there's this one. Do we know this one? Do we know what it's called? The purple one?
No.
It is called an absolute value, and we'll get to it. Looks like a V.
Oh, okay.
It will always pass a vertical line test. This one, not so much. Well, actually, the one I'm about to show you will. There we go. Will that pass a vertical line test?
Yes.
Looks like a sideways parabola, doesn't it?
Inverse?
It's a root. Yeah, it's the inverse of a parabola. It's a root. So square root of x. But it will pass. Now, you don't have to memorize this. These are just standard functions that will always pass a line test. This is a reciprocal. This is an exponential. This is a decay. Don't worry about any of them for now. But they will all pass a vertical line test. And I'm going to send this to you so that you know things that pass a vertical line test. It's always good to study your parent functions because they will come up throughout. See? They will come out up again and again and again. So let's go back. So they're asking us to always spot a function. Is that what kind of graph will that make?
That's a line.
Yeah, so it will always be a function, so long as it doesn't say x is equal to a number. This is -4. What does it lead to?
0.
That's the x, and that's the y. And this, do you see any of the x's repeating?
No.
Therefore, this is a function. It's okay if the y's repeat, but the x's should not repeat and lead to a different y value.
Okay.
Hang on. All right. What kind of graph is this? This looks like something we might have just covered.
That's a parabola.
Yeah, its face is downwards because this minus,
Downward.
but therefore it is a
Function.
right. Now, let's see if we can spot this. This is a funny looking thing, but it's very similar to the thing we just looked at.
Yes, a parabola.
It is indeed a parabola. But now it's asking for domain and range. What the hell? So, domain and range are, I'm just going to go back to that parent function, also explained in here. The domain of a line is x goes on forever and y goes on forever. But the domain of a parabola is x can be any value, but y, it can only be the value of the vertex. So we would need to know the vertex to figure out the domain and the range of this parabola. Let's cheat a little bit. Let's put this into Desmos. Always use your tools at hand when you're studying, okay? Always use your tools. So there we have a very terrible thing. We're going to do 5. I think it was x minus 2 squared. Just going to go back. It's -2 plus 1 minus 3. I was very close. Okay. And we're going to just look at the vertex. We can see the vertex on the graph. What's that number? Let's go back to it. Right there.
-1, -3.
Yeah, that's the vertex of the parabola because it's the very top of it. Why does this parabola face down?
Because it's negative.
Yep.
The beginning is negative.
Anywhere in the equation, can I see a 1 or a 3?
Well, yeah, the +1 -3.
So it looks like this one exactly matches the y value of my parabola, right?
Mm-hmm.
Looks like the reverse of this, instead of +1 -1, matches the x value, doesn't it?
Yes.
This is called vertex format. There are 3 formats for a parabola, and this is one of them. The nice one about this is the vertex is right in there.
Yeah, it's given to you.
Yeah. You just got to memorize, oh, that's opposite for the x. -1 for that. But since we're determining range, and range is a y value, do you know that?
Yes.
Domain means what possible x values are there, and range means what possible y values in this graph. You see anything in this graph above -3? Is there anything up here?
No.
No. So the range doesn't exist for this graph. But I can see a -3, right?
Mm-hmm.
There's a -4 around there if I can get my thing right on it. And looks like there's a -5 and -6. It keeps going down and down and down. Looks like it keeps going down forever. So that means this range, write this down, the range for the parabola is -3 or lower. -3 or lower. We would write that like this. We would write that like this. Y, we would say first y can be any real number. We say ER. But y is smaller or equal to -3. Why do I have to put that equals there?
Because like the vertex is -3.
That's right. The vertex is included. So it exists at the vertex. So -3 must be included because -3 is its vertex. So you wouldn't say smaller than -3 is the range. You would have to say smaller or equal to -3 because -3 is the exact vertex.
Okay.
So now we can determine the range of a graph of a parabola if we have it in vertex format. That's how we recognize if it's in vertex format. We got a bracket with a square. The number in front's not important except whether it faces up or down. This down is important because it means the range is down, smaller than. What if that minus wasn't there? What would our range be? Let's have a look. Uh-oh. What's our range on this one? See if you can tell me. I'll let you know that this is still -1, comma, -3 at the vertex. So what's the range?
The range is y is equivalent to real numbers. Y is greater than
Yeah. Or
equals
yeah,
-3.
that's right. In this case, we're starting at the vertex and we're going up. So that plus or that minus can really tell me which way the range is going. If it's minus, it's y is smaller or equal than. If it's plus, it's y or bigger or equal to. The importance of range is just to allow us to know what possible numbers there are. Just like I didn't include some of the days of the week last time, we can only use those 4 days of the week to predict.
Mm-hmm.
So let me ask you something. Now that we have a technique for parabola, if we can't graph it, but they give it to us in this format, we can determine the range, can't we? Because we know if it's a negative number, it's going to be smaller than, and we know that this is the y value of the vertex. And that's all that matters for range. For domain, for all parabolas, XER, X can be any number. For all parabolas, XER.
Mm-hmm.
So if we can kind of memorize the domain and range of typical parent functions, we can usually come up with it. This is kind of mean that they threw that right in there, so we're going to skip it. But these all look, if you look at my parent functions, I'm going to tell you that all my parent functions are functions. All my parent functions are functions. And I'm going to tell you whether these are parent functions or not. Is that a parent function? Is that a function? Did we determine if this is a function?
Yes, it's a function.
Because it's a parabola. This is a reciprocal function. They look funny, but I'm going to tell you it's one of my parent functions. Let's have a look. We'll just do a different one instead of what they have. It looks like that would pass the vertical line test. You might think, oh, it doesn't right there, but it does. It doesn't ever repeat, but it does. It looks funny. So that looks like it's a function. You can always graph them to see. This is a growth function. This is a growth function. I can tell because x is an exponent. X is an exponent. 2 to the power of minus x. 2 to the power of minus x.
Wait, hold on. Wait,
yeah.
What, Mom? No. Wait, what is she doing where? What is she doing where?
Wasn't she here?
Where is she now?
I don't know. Her phone said she's in the house.
What the heck? I don't know. Sorry, PNC's missing right now.
Okay. If she needs your help, let me know.
Okay.
Are you going to stay here or are you going to go help your mom? Okay, good.
Continue, Pete. You can continue.
Yeah, I'm just answering a text. Okay, let us continue. This is a cos curve. It's also going to be a function, but this looks familiar to something we did earlier. See if you can remember that, because I drew this exact one. Do you remember what that was?
The wait, sorry, Pete.
Yeah,
Sorry.
I know.
What, Mom?
Huh?
What'd you say?
No, she never replied.
I don't know where she is. I don't know.
No, I know, can you just text her, weren't you guys supposed to do stuff today?
Yeah, we were. Let me text her then.
Yeah.
She's probably asleep.
Okay, are we ready?
I'm just sending a quick text again to you. Okay.
What was you doing and out?
I don't know where she was going. I don't know. Okay.
Okay.
I'm gonna continue with Peter.
Okay.
I'm studying for math. I'm gonna
Yeah.
continue. Okay, continue.
Okay, I'm just waiting. Do you remember we drew this? Do you remember what it looks like?
Oh, you're talking to somebody.
It was to Peter. We're studying for math. Okay, continue.
We actually drew this one. Do you remember what it was? This one right here.
Oh yeah, a circle?
That's right. Will that pass the vertical line test?
No.
No, it won't. So when we get used to memorizing, not memorizing, but having a good idea, get off that. There we go. We'll start to realize, oh, that's one of the parent functions. 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 We'll be able to say function, that's a 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 function. And then when we come here, we'll go, oh, that's a circle. That's not a function. So this is just a matter of studying your parent functions, and I don't want to get into it just yet. Let's determine if these are functions or relations. By the way, a relation is one where the x repeats. A function is where the x doesn't repeat. This number 1 leads to what?
To 2?
Yeah. Oh, let's do a faster way. Do these x's ever repeat?
No.
It's a function then.
Function.
Even though this 3 leads to 4 and this 5 leads to 4, if we were to graph that on our graph, 3 comma 4, 5 comma 4, this will clearly pass a vertical line test. This will clearly pass a vertical line test. That's because it can cross through that only once and cross through that only once. Let's reverse that. If this said 4 comma 3, and 5 comma 3, or hang on, 4 comma 5, 4 comma 5. Do you think that's going to pass the vertical line test?
No.
No. They've both got an x of 4. 4 repeats. Leads to 2 different y's, but at 4 repeats.
So we'll not pass the vertical line test.
Nope. So that means if the x repeats, it's not going to pass the vertical line test. If the x doesn't repeat, it will. And that's a faster way of memorizing it. So let's look at these x's. Do they ever repeat?
No.
Function. Do these x's ever repeat?
No.
Function. Let's see if these x's ever repeat. 2, 1, 5, 0.
No.
Function. 2, 6, 2.
2.
Hey,
it's not a function.
That's because this 2 leads to the y of 5 and this 2 leads to the y of 7. So we can't tell if it's Saturday or Tuesday.
Mm-hmm.
Okay, let's go to this one. 1, 2, 3, 4. Do the x's repeat?
No.
Function.
So it's a function.
What if we did the vertical line test here? What if we did the vertical line test here? What if we did the actual image that's on the screen here? There we go. Let's do the vertical line test. Function?
Yes.
Function?
No.
No. Good. What the hell is this? What the hell is this?
Inverse parabola.
Huh. Is
Oh,
it?
x squared
Is it
equals
though?
2y.
Is it though? So what if? How would we get? Here's a good thing to practice anyway, Natalie. See this there?
Yes.
Do we ever see x is equal to something? Isn't it always y is equal to something?
Yes.
Okay. How would I get y all alone? Well, we're going to list
You're
what
gonna have to isolate it.
we're going to have to isolate it. But to do a really good job isolating, let's list in order of bed mass everything that's happening to y. Do we see any brackets happening to y?
No.
Do we see any exponents over y?
Over y, no.
Let's get rid of it. Yeah, we're focusing on isolating y. Do we see anything multiplying or dividing y?
No.
Are you sure there's not anything multiplying y? What happens when there's a number
Oh yeah,
right?
there's something multiplying.
Yeah, what is multiplying?
2.
So in bed mass order, 2 is multiplying y. That's the first thing that happens in bed mass order. Now we're done division and multiplication because there's no more things multiplying y. Is there anything adding to y or subtracting? Yeah. So we would list that in bed mass order. Step 2. 1 is being added to y, to 2y really, but we'll just say to y. Now we're going to reverse that starting with step 2. We're going to reverse that starting with step 2. What's the reverse of 1 added to something?
The reverse of 1 added something?
Yeah, see step 2. See step 2 above. What does it say? 1 is being added to y. What's the opposite of 1 added to something?
Subtracting something.
So we're starting with the bottom step, number 2. Yeah, but if I'm adding 1, what should I subtract?
Subtract 1
Subtract 1 from both sides.
from both sides.
Yep. When in chemistry and math, you have to do it to both sides of the equation. Okay, that's step 2. Now we go up to step 1. What is the opposite of 2 multiplying? Something being multiplied by 2?
Dividing?
We're going to divide both sides by 2. So it looks like up here, I listed everything happening to y in bed mass order.
Mm-hmm.
And then down here, I started with number 2, and I reversed the mathematical operation on both sides. Then I went up the list to number 1, and I divided both sides by 2. So I reversed this list and did the opposite, right?
Mm-hmm.
Okay. Can you follow the green step 1 for me? What does it say?
Subtract 1 both sides.
Okay, we're going to subtract 1. We're going to subtract 1 from this side. And we're going to subtract 1 from this side. Great. All right, what happens 1 plus 1 minus 1?
0.
Yeah, that's why we did it. We're done step 1. What does step 2 say?
Divide both sides by 2.
So if I divide this by 2, and by the way, I should put all this in a bracket over here, and just divide it by 2. What happens to this 2 divided by 2?
It's gonna go away.
It's going to become 1 or just go away because we never just put a 1 there. It looks like we have the y isolated, right?
Mm-hmm.
So we did a correct thing here. I'm going to teach you one other method instead of dividing by 2 that might help you. Instead of dividing by 2, we're going to multiply by the reciprocal. So 2 is being multiplying y. We're going to multiply by 1 over 2 on both sides. This 1 over 2 is the same thing as dividing by 2, because when it multiplies, this 1 multiplies the 2y, and this minus, or this division by 2 is multiplying whatever's down here, which is 1. And it's the same thing. It ends up canceling out. But over here, it's a lot cleaner. Over here, it's a lot cleaner to multiply this by a half than it is to put the 2 underneath it. And I'll show you why. We now have this. Y is equal to a half times x squared minus 2. What does this look like? What kind of function does this look like?
It looks like...
The hint's right there.
Oh, the parabola?
It's a parabola. Is a parabola a function?
Yes.
Yeah. So we had to spend a little time to figure out what's going on here because all our functions are always y is equal to something. So it's kind of hard to figure out until we isolate y, what kind of function it is. But it looks like this crazy mess right here. Yeah. let's go with that. This crazy mess right here that doesn't look like a parabola, it kind of does, is indeed a parabola. Let's look at this one. This one's a cheat. Be careful of this one. How would I isolate x or y? What's happening to y here? What's happening to y?
It's being x squared.
Yeah, it looks
So
like
you have to-
looks like it's e, isn't it? E,
Yes.
exponents. So y is being squared. Now we only have the one thing happening to y, so we're going to reverse that. What should we do?
Square root it?
Yeah, we're going to square root both
sides.
sides. Now, here's the bad trick. Whenever you square root something, or have to square root something in a mathematical operation, sure, this square root over here is going to get rid of the square. They're going to cancel. But over here, when I square root x, I have to put a plus and a minus. What the heck, Pete? Why?
Yes. I actually don't know why.
Here you go. I can
But I
explain
know
it.
you have to do that.
What's the square root of 9?
3.
Yeah, that's because 3 squared is 3 times 3. It's 9, right? But here's why you add a minus. Minus 3 squared is the same as minus 3 times minus 3. And what is that equal to?
Negative
Oh,
9.
we have a negative times a negative.
Oh, sorry. Positive 9.
Yeah, didn't I also get 9? Negative 3 squared and positive 3 squared both lead to 9.
Yes.
And that's why the square root of 9 is positive or minus 3. Because squaring a minus 3 gives us 9. And squaring a positive 3 gives us 9. So the square root of 9 has 2 possible answers. The square root of y squared has 2 possible answers. Let's go see what this looks like on Desmos. We'll put it in the original format. Y squared is equal to x. Will that pass the vertical line test?
No.
No. Now let's look at it in our version. Negative square root of x is one of them, and y is equal to the positive square root of x. Desmos doesn't let me draw both of them at the same time. Well, there is a way, but I'm too lazy. Does that pass the vertical line test once we made it plus or minus square root of x?
No.
No. So that is not a function. But it took a little bit of work to figure that out, doesn't it?
Yeah.
Right. This one
Wait,
looks...
so
yeah? So,
if something is always x equals, it's not a function. It's
no, that's not true, because when we did this one, it was a function.
Oh, yeah, that's true.
That's not true. The problem is we've got to figure out what y is equal to, because all functions are y is equal to. This one's weird looking. Let's just cheat and see if that's a function. Okay, let's get rid of that. That looks like a function. Yeah, that's our old function. It's called the reciprocal function. So that's a function. We just have to recognize it. What about this one? That looks familiar. Instead of f of x, just say y. What is that?
It's a function.
Yeah, y. What kind of function is that? What kind of graph?
That's a parabola.
No, do you see a square there? You see a square?
Oh.
No square.
Sorry, it's a line.
It's a line, and all lines other than vertical lines are a function. So that's all that functions are. They're just a way of seeing what leads to what. Oof, boy, that's a brutal one. Let's not do that. Let's see. Okay, no, we're going to skip that. Your teacher went right to this.
Yeah, y to the power 4.
Mm-hmm. Did she assign any questions?
No.
So whenever you get an assignment of questions, I want you to send a photo of it to me. Okay?
Okay.
Then I want you to try them. And then I want you to say, okay, Peter, I didn't get it. Here, they're going through the parent functions that I went through. So I'm going to send you the link because it describes what kind of function is this. Just pretend instead of f of x, it says y is equal to x. What kind of function is that? What do you think?
That's a line?
Yep. What kind of function is that? Yeah, so these are all functions. That's a reciprocal function.
Okay.
1 over
reciprocal.
x, yeah. This is, it has an absolute value on either side, so it's going to look like a v. Is that a function?
Okay.
This is the
Yes.
square root. You might say, Peter, didn't you show me the plus minus square root was not a function? You are right, but this is only the plus side of it. So it is a function. Just-
It is. So it's if a negative side.
if
it's
it
not a
had,
function.
no, if it had plus and minus. Negative is still,
Oh.
negative is still a function. Here. That's still a function.
Oh.
But when
okay.
it's both plus and minus at the same time, it's not a function. So it's only when you solve for y that you can figure out if it's a function or not. But as they've given it to us, that's a function. This is a exponential curve, 2 to the x, and this is a sine curve. So essentially, they want you to get used to these 7 functions and just sort of get to know what they look like, their domain, and their range. If we look carefully at the parent functions, I'm going to turn on all the ones that they've described. You can see them. We're skipping those. Ooh, it's looking messy.
Those notes look really good. Pete, can you send those to me?
That's
as
what
well?
I'm going to send to you. As a matter of
Thank
fact,
you so
I'm
much.
going to send it to you right now. As soon as I see my name, sometimes it's got, you know what I'll do? So just close it because I can get, for some reason, Desmos is not showing me my little top thing. And I want to be able to show you open graph. And there should be a way to. There used to be a little thing up here. I seem to have gotten rid of my bars because I know I can send it. Maybe I can just send it like this. There we go. Yeah, you got to get rid of that fabulous world. It's all jammed up.
I know it is all
Functions.
jammed up.
So the main ones that we're going to study are line, parabola. Those are the 2 big ones. Then we're going to do absolute value, reciprocal. That's like 1 over x. Sine, wave. Looks like a wave. And what was the last one they gave us in the textbook here? Sine wave. Oh, exponential. Yeah, and square root. And square root. We got a square root. Square root is also called radical
Okay.
or radical. And reciprocal, 1 over x, growth, 2 to the power, and sine wave. There we go. See if that works. Looks like it will. If it doesn't, let me know.
Okay.
I know there's a way I can just send it to you. Just for some reason, the little send button's not appearing. I got to fix my Desmos. I clicked something that got rid of the top part. Okay, so we're about an hour in, but I just want to cover a couple more things. They obviously want you to study the domain and the range. So domain is XER for this one. This one has 1 exclusion on the XER. This is, I'm just going to show you the XER. XER, absolute function. XER, parabola. XER, line. No.
Okay.
XER, growth. XER, sine. So only the radical and the 1 over x are not XER. Range.
What would those be?
Yeah, I'll show you. 1 over x, radical. Let's do this. Here we go. Y is equal to 1 over x. Well, it looks like, do you know division? What can't you divide by? What number can you never divide by?
0?
Yeah, that means x can't be 0 here, can it?
No.
So that means if I drew x is equal to x equal to 0, that graph never crosses that blue line. Looks like it down here, doesn't it? But if I zoom in, it doesn't cross that blue line. That's because I can never put a 0 down here. My calculator will explode and the shrapnel will kill everybody in the room. So never put a 0 in your calculator. So that means in this case, XER, but x can't be 0. So that's the only exception to the range here. But it also looks like y, ER, but y can't be 0. And that's true. Why can't y be 0? Because there's no value of x that I can put in here that will make the result 0. There's no value of x I can put here that will make 1 over x 0. There's nothing. I can't put a 0 for x because the shrapnel will kill everybody. So that means if I put x, even if I put x is equal to 0.00001, y is like 1,000,000. If I put 1 over 1,000,000, y is very close to 0, but it's not ever getting there. See? It's a very small number. So that means there's no number for x I can put in that y is equal to 0. So that means xer, yer, but x can't be 0 and y can't be 0 for a reciprocal function. And that makes sense when you understand you cannot divide by 0. And so as a result, there's no value of y that can become 0. Make sense?
Yes.
Let's look at what the other one, why the other one can't be xer. Well, it looks like the x starts here and goes to the right. And that's because I can't put a negative number in a square root. I can put a 0. Square root of 0 is 0. But I can't put -1 or the shrapnel kills everybody. So never put minus. See, it says undefined. So that means this one, x must be bigger or equal to 0. That's the domain of that one. Sometimes it's not always that way, but this is the parent function we're talking about. But if I were to put a minus here, a minus in here, it's on the other side. You might say, Peter, you told me I can't square root of minus. You're right, I can't. I can't. But you see, I can do square root of minus, and if I make my x -3 or -4, suddenly that minus times a minus makes a +4. And the square root of +4 is 2. So that minus here allowed all my minus x's to exist. Because a minus times a minus x will make a positive number, which will give me a square root. So you can see I'm only talking about the parent function, and they only want concern with the parent function. Just be aware we can do what's called transformations of parent functions, and we can make them face all sorts of different ways. But the parent function is what they want you to learn. And for this parent function, xer, x is bigger or equal to 0. What about y? Well, it looks like the y's are only above, right? Y is bigger or equal to 0 as well. Because there's no value of x I can put in here that will square root and give me a negative y. There's no value I can put in for x. That'll give me a negative answer. Because you can't square root anything that results in a negative answer. So all my y's will be positive as well. So that's an exception to the domain and range rules. And they're all in those notes I gave you. So y is equal to sine x. It looks like that. Looks like xer. Yep. Xer. But it looks like it only goes so high. If I look at the y value, it only goes as high as 1 and as low as -1. That's the sine curve. It's used in electrical engineering. And that means for the sine curve, domain goes on forever, xer. But range is -1 is smaller than y, smaller or equal to y, which is smaller or equal to 1. That just means y falls between -1 and 1, but it can also be equal to them because this is a 1. This is a -1. So that means the range of a sine curve falls between -1 and 1 and can include 1 or -1.
Okay.
So range is unique for that one. So you can see you just got to sort of memorize the parent functions. Most of them are easy to memorize. And then it's just a matter of sort of understanding, okay, we're going to skip what that means. Intervals of increase just means when is this graph going up? When is it going down? When is it going up? For instance, a line like this is always going up. So its interval of increase is every value of y. And a line like this is always going down. So it only has intervals decrease. But a parabola is going down here, right to the vertex, and then it's going up. So its intervals of decrease are all the way to here, and its intervals of increase are all the way to here. And that's defined as x smaller than 0, x bigger than 0. You can't include the 0
It's like
because,
the maximum and minimum.
well, sort of, yeah, that's the minimum right there. But this graph is going downhill, like it's going down a hill. What that means, it's decreasing.
You know what I didn't really understand? That one
Yeah.
thing that my teacher did when it came to like a parabola is that whenever we were doing like domain and range, she would often do like negative infinity plus infinity.
There you go. Okay. So all graphs are read from left to right. And if I zoom out on this graph, it doesn't look like the parabola is going all the way to infinity over here, but it is. It looks like it's just stuck there. But I can put any value of x in there. I'll give you an example. So this graph is a parabola. It's the parent function graph of this. Oh, please. There we go. Of this. And the formula is y is equal to x squared. Well, I can put negative a million in for x. Negative a million in for x. Here I go. Million. Hell, I can put huge. Boom. And if I square it, I get a value of y. So that means I could put any value of x in there. It's going all the way to negative infinity. I can put any value. And since I don't want to keep saying negative 10 billion, I would say, okay, I can go all the way forever. And then I can put any value of x that's positive. I can put a million in there, or a billion, or a trillion. I can just keep slamming zeros in there. And once I square it, I'll get an answer. So that means it's possible to put positive infinity in there. So sometimes when you want to outline when things are happening, for instance, this is going down, right? It's going down. It's going down right until it reaches 0. So I would say the range of when this graph is going down goes from minus infinity all the way to 0. And you would describe it like that. I think they use round brackets. So that's just saying from negative infinity to 0, this graph is going down. What do you think I would say? What do you think I would say for going up?
You'd say 0.
Yeah.
Well, wouldn't it be square bracket actually for 0 since it's a given?
But the problem with the exact 0, at 0 at the vertex, it's flat. It's not going down or up. So you cannot include the 0 in the vertex or the increase because at 0 we're flat.
Okay.
So
So then it would be square bracket. I mean circle bracket.
Yeah.
And then 0 plus infinity.
Yeah, 0 comma plus infinity. That's just a way of saying interval in a faster way. It's saying any values of x between 0 and infinity. And another way you would write that is 0 smaller but not equal. X smaller but not equal because you can't include infinity. Positive infinity. This is the same as that. This is faster. This is
That's
long.
integral notation.
Yeah.
And the other one is solution set.
Yeah. And you can do it over here too. Minus infinity is smaller than x is smaller than 0. And you can't include the 0 because it's flat, and you never include infinity. Infinity is never included. It's just a rule. But there's always these little nitpicky rules. So we sort of covered that. It's not too important. Some of these they have missing pieces. Some of these have missing pieces. Well, parabola doesn't have a missing piece. A sine curve doesn't have any missing pieces. An absolute value function doesn't have any missing pieces. But the reciprocal function has a missing piece right here and right here. That's because you can't have an x value of 0. So it has what's called a discontinuity. It doesn't continue from the red graph here, never connects with the red graph over here. So they're disconnected or discontinuous. This is one of the few graphs that's not connected. Okay, so we're going to keep going. 0. So that means when x is 0, what is y? So that's just a matter of memorization. So in the case of the reciprocal, x cannot be 0. So y cannot be 0. But in the case of a parabola, when x is 0, what is y?
Y is 0.
Right. So the zeros are 0, comma 0. What about a line like this? When x is 0, what is y?
0.
Yeah, so it looks like it's 0, comma 0 is its zeros. Sometimes lines don't match that, though. Oh, look at this line. It's up here. When x is 0, what is y?
Y is 5.
Ah. When y is 0, what is x? When y is 0, so if I put a 0 here, what is x? How do I solve that?
Wait, when Y is 0, what is X?
Yeah, because that's the other 0. Zeros are when x is 0 and when y is 0. How do I solve that? What's happening to x?
It's being added 5.
5 is being added to it. How do I reverse that?
You subtract it.
On both sides, right?
Both sides.
What's 5? You always have to do both sides. What's
Oh.
5 minus 5?
0.
What is 0 minus 5?
Negative 5.
Oh, looks like when y is 0, x is negative 5. Let's see if that's true for the line graph. Bring the line graph back. Yeah, plus 5 I had. Yeah, it looks like when y is 0, x is minus 5, and when x is 0, y is 5. So those are the two zeros for this particular graph. Now, for the parent graph, it's just 0, 0. But I wanted to show you that sometimes the transform graph have different zeros, and what you do is you put a 0 in here and solve for y. You put a 0 in here and solve for x.
Okay.
Just don't worry, it all comes. Y-intercepts are the same thing as the 0. Okay, zeros, they mean when x is 0, and y-intercept, they mean when... No,
Y
sorry,
0?
hang on. Y-intercept when x is 0. Y-intercept is when x is 0, and 0, I guess, is when y is 0. No, that's kind of a weird way to say it. I think zeros just mean when they're... I think zeros just... It's easier just to think of zeros as when y is 0 and then when x is 0. Symmetry. Symmetry just means if it matches or is mirrored. There's some obvious symmetrical ones. This parabola is symmetrical. This line right in the middle acts like a mirror. This line right in the middle acts like a mirror. So it's easier to see if it's red. No, that's not a mirror. That's a mirror. It looks like it mirrors through this line. What is this line?
It's vertical line.
Yeah, but what does it happen to lie on? It happens to lie on this
0.
black line, which is called
The Y-intercept.
Y? Not quite.
Intercept.
Nope.
No?
The whole line is
Y.
called something else. The whole line is called the y-axis. So that means that means parabolas are mirrored or symmetrical through the y-axis. Because pretend that the y-axis, when x is 0, is a mirror. And that means it's mirrored on each side of that. Let's have a look and see if there's any other mirrors. I'm just going to throw one out. Yeah, well, this is technically a mirror. And the mirror that it's reflecting through is this one.
Mm-hmm.
It's as if it's looking into the mirror and seeing itself on the other side. That is symmetrical through this line. Kind of weird to think of it that way. So I don't think your teacher wants that depth. But some things are symmetrical and some things aren't. End behaviors just means what happens way to the left, what happens way to the right. Well, a normal line, we can see on the left, it's going way down here in the y values. So when x becomes negative infinity, what does y become? When x becomes negative infinity?
Positive infinity?
Oh, you see positive y's there?
Wait. Sorry, could you ask me one more time?
When x is negative infinity, in other words, way to the left of this graph, where's y going? Where are we down here? As I go down on the left of this purple graph and go make all my negative x's, what does y become?
Negative as well?
Yeah, so that means the end behavior is this. As x approaches negative infinity, y approaches negative infinity. When x approaches positive infinity, let's have a look. Where's y going when x approaches positive infinity?
Oh, positive.
Yeah, looks like for line, for y is equal to x, y is approaching positive infinity. That's end behavior. This is the left end behavior, and this is the right end behavior. The left is always when x approaches negative infinity. Y, you figure out y. Now you can plug that into the graph, into the formula though. If I put negative a million in for x, what is y in this formula? If I put a negative million in for x, what is y?
A negative.
Negative million.
Well?
Negative million. So that tells me when x approaches negative infinity, y is also approaching negative infinity. Not so for a parabola. Not so for a parabola. Don't worry, we're almost done. And a parabola looks like, oh, that's a terrible drawing. Looks like as I go way left on my x values, way negative on my x values, y becomes what?
Positive.
Yeah, and I can prove this by putting a huge value of negative for x and squaring it. Tell me what the y is here. Is that positive?
Yes.
Yeah, so as x approaches negative infinity for a parabola, so for a parabola now, as x approaches negative infinity, y approaches positive infinity. What about when x is positive, way on the right? When I go way up here on my positive axis, what does y approach?
It's still positive.
Yeah, it's still positive infinity. So if I put plus a million here, I get still a huge positive y. So that means as x approaches positive infinity, y approaches positive infinity. This is end behavior. This is what happens way on the left of the graph, what happens way on the right, and if instead of infinity, you can just put a big value of x and solve for y if you're confused.
Okay.
About this one, what happens as I go way left? This is an interesting one. What happens as I go way negative on the x? Look at the y values. Oh, it's hard to see. Let's put in a value here. What's a good big negative number to put in for x?
Negative
Like a million, right?
57. Oh,
Yeah.
yeah.
Well, let's say 1,000. Yeah. What's going on with y? What number does it look like it's approaching? What's going on? Looks like it's getting closer to what?
To like 1.
No. Does that look like it's getting closer to 1?
No.
What's going on with that? What is that number? That's like a very small number, isn't it?
Yeah, it's getting closer to 0.
Yeah, it's getting closer to this line right here, which is y is equal to 0. So it's approaching 0, but looks like it never reaches it. So that means for a reciprocal, it's a weird one. As x approaches negative infinity, y is approaching 0 from the negative side, which means from the bottom of the graph. You see, we're on the bottom. See how our y values are all negative? That's because 1 divided by a negative number will always be a negative number. I also want you to learn this little trick. Whenever I divide by a big number, 1 by a big number, my result will be small. Whenever I divide by a small number, my result will be big. So whenever you divide by a small number, 1 divided by a small number, let's have a look. 1 divided by 0.0001, I get a big number. Whenever I take 1 and divide it by a big number, I get a small number. Those are called reciprocal. It's the reverse result of what you put in. But let's look at the far right side. As x approaches positive infinity, what is y approaching? Let's figure that out. I can just put f of x in here instead of y. And then down here, I can let it solve it for me by putting f of positive a million. What is y approaching? Put some more zeros.
0.
Yeah, 0, but is it positive or negative?
positive.
Yeah, so it's approaching as x approaches infinity, positive infinity. Y is approaching 0 from the positive side. I think it's written like that, actually. Y is approaching 0 from the positive side. That's interesting and just something to get used to for your specific parents. So it's really what they're trying to make you do is understand the main parent graphs and how to do it. I think that's
That
a
is
lot.
1 point.
That's
That's
1.4. I jumped to 1.4 because your teacher jumped to 1.4. So clearly she wants, here, look, they even outline it in this book. I'm going to send you this book
Yeah.
because they tell you they're the answers to various things here. They kind of outline it. You'll always find an example in the chapters, and I'm amazed they don't give you a textbook because it's a lot
Yeah.
easier to have a textbook because there's always examples. They've taught strictly from notes. Sometimes they don't let the students bring any notes home, and it's really weird.
Oh,
Do you feel that you learned anything?
today in this.
Yeah.
Yes. I
Now
think
it's a
I have.
flood of information, so I've recorded it.